Imagine for a second that you're standing in the middle of a massive stadium. It's a concert. You know that moment when the band slows things down?
Oh yeah, the ballad moment.
Exactly, the ballad moment. The lights drop, and the lead singer steps up to the mic, wipes the sweat off his brow, and asks everyone to take out their phones. "Shine your lights," he says.
It's a classic moment for sure.
It is, and just instantly, 50,000 tiny lights flick on. In, the blink of an eye, the dark arena is just filled with this swaying, artificial, starry sky. It's this sea of invisible hands holding up these little stars. It's beautiful, right?
It is a powerful image. It really gives you this visceral sense of the sheer scale of the crowd.
Exactly. Now, the book we are diving into today opens with that exact image, but it asks us to go bigger. Much, much bigger. Imagine if that lead singer could snap his fingers and command every single smartphone on Earth to light up at once. That's 7 billion phones.
Which is what, roughly 85% of the entire human population holding a light? That's staggering.
Right. But don't stop there. Yeah. Keep the visualization going. Imagine if every chip in every single device in the world lit up at that same moment. We aren't just talking about phones anymore.
No, not at all.
We're talking laptops, Wi-Fi routers, the dashboard of your car, the traffic lights down the street, your washing machine, the pacemaker in someone's chest.
You're talking about the servers in the data centers holding your photos from 10 years ago.
No.
The chips in the radar tracking a plane, and the chips in the flight control system of the plane itself.
Exactly. If all of those lit up, the entire world would just be glowing. It would be this web of light wrapping the entire planet. And here is the kicker, the thing that really stops you in your tracks when you start this book. Almost all of the advanced chips that make that world function, the ones doing the heavy lifting, they are made using machines from one single company. A company located in a small, quiet provincial town in the Netherlands called Veldhoven.
A company that for a very, very long time was arguably the most important tech company you had never heard of. We are talking, of course, about ASML.
ASML. Today we are doing a deep dive into Focus, The ASML Way by Mark Hijink. And I have to be honest, before reading this, I knew they were big. I knew they made chip machines. I did not realize that without them, the modern world basically just, it stops.
And that's no exaggeration. If ASML disappeared tomorrow, the global economy would grind to a halt within weeks. We're talking about a monopoly on the most complex machine humanity has ever built, a machine that really keeps Moore's Law alive.
And because of that monopoly, this Dutch company has moved from being this, obscure background player to the absolute dead center of a geopolitical firestorm between the U.S. and China.
It's Europe's most valuable tech company yet. And this is the best part of the origin story. It started with a leaky roof and a business plan that everyone, and I mean everyone, thought was hopeless.
That's what I love. So our mission today is to unpack this properly. How did a hopeless spin-off from Philips become the absolute linchpin of the global economy? What is this ASML way of brutal honesty and constant firefighting? And seriously, I want to understand how this impossible machine actually works.
It is a story of impossible physics, high-stakes finance, and some very, very loud shouting matches.
I do love a good corporate shouting match. But let's start at the beginning, section 1. The origins. Because this didn't start as a trillion-dollar idea. It started as a headache for Philips.
A massive headache, yeah. To understand ASML, you have to go back to the 1970s and the Philips Nat Lab, the Naturkundig Laboratorium.
So this was kind of like their Bell Labs.
Exactly like the Bell Labs of Europe. This place was legendary. It was a paradise for researchers. You had brilliant scientists who were basically given free rein to invent the future. They weren't worried about quarterly profits. They were worried about the laws of physics. And in the early 70s, a group of them invented something called the silicon repeater.
Which is the great-grandfather of the machines we're talking about today.
Correct. Later, it became known as the wafer stepper. The basic concept is photolithography. You're using light to print these tiny, intricate patterns onto silicon wafers to create the pathways for electricity, the chip. The scientists, guys like Steve Whittecock, they saw the brilliance of it. They realized this machine could be more precise than anything else on the market because of the optics. But here is the problem. Philips wasn't a research lab. It was a massive bureaucratic conglomerate selling light bulbs and TVs.
So the scientists see this incredible breakthrough, and management sees what? A bill.
A money pit. A distraction. You have to remember, building these lithography machines is astronomically expensive. And in the late 70s and early 80s, Philips was bleeding money. They were fighting off the Japanese electronics giants like Sony and Panasonic. They just didn't have the patience for a long-term science project that might not pay off for a decade, if ever.
And from what I gathered in the book, it wasn't just that it was expensive. The early prototypes, they weren't exactly ready for prime time. I read about the oil table failure. Please walk us through that because it sounds like a complete disaster.
Oh, it's a classic example of the gap between a lab prototype and an actual commercial product. So the PAS-2000, one of their early machines, needed to move the silicon wafer very, very precisely. To do that, they used hydraulic motors,
Hydraulic, as in powered by fluid.
powered by oil. Now, where do you make chips?
In a clean room.
In a clean room, a room that has to be thousands of times cleaner than a hospital operating theater. A single speck of dust can ruin an entire chip.
And oil is, well, it's messy.
Oil leaks, oil fumes.
Yeah.
The PAS-2000 was practically spraying an oil mist. If you put that machine in a clean room, you destroy the clean room. It was completely, utterly unsellable. It was a joke in the industry. It highlighted that Philips had great science, the optics were good, but they had no idea about the customer's reality.
So management is saying stop throwing away money. They want to kill the project, but it didn't die. Why not?
Because of a few incredibly stubborn individuals. You had Wintrust at Philips, who just refused to let it go. He was told to stop, and he essentially hid the budget to keep it going.
He was cooking the books.
Pretty much. He was shuffling money around in the account so the bosses wouldn't notice he was still funding these steppers. And then you had an outsider enter the picture, Artur Del Prado.
The founder of ASM International.
Right. And Del Prado was a character. He was the complete opposite of the Philips bureaucrats. He was a trader, an entrepreneur. He'd spent time in Silicon Valley back when it was just starting to be called Silicon Valley. He saw what Philips missed.
Which was?
He believed that the future wasn't just in making the chips, but in making the tools to make the chips. He basically badgered Philips until they agreed to a joint venture in 1984.
And this is the birth of ASML. Philips puts in some money, ASM puts in some money. But they almost named it something truly terrible, didn't they?
They did. The working title was ALS, Advanced Lithography Systems.
Which, yeah, not great.
Until someone, thankfully, pointed out that ALS is a devastating motor neuron disease.
Branding crisis averted. Just barely.
So they switched to ASML. But the start was so rocky, we have to talk about what the employees called the deportation.
The deportation, that's a really strong word.
That's what they called it. Philips forced about 40 engineers to transfer to this new joint venture. These guys were Philibert lifers. They had great benefits, job security, a solid pension, access to the prestigious NatLab campus.
And
Suddenly, they're told, you don't work for Philips anymore. You work for this risky startup now. They lost their benefits. And physically, they were moved from the high-tech campus to this temporary building just outside the gates.
Describe this building. Because temporary building can mean a nice modular office, or it can mean, well, a shack.
It was a shed, literally a leaky shed. There are stories of engineers working on these incredibly precise optics equipment worth millions while holding buckets to catch rainwater dripping from the ceiling.
No way.
Yes. The wind blew through the cracks in the walls. It was miserable. They were angry, they felt abandoned, and they were working for a company that everyone in the industry expected to go bankrupt within a year.
That is the definition of a humble beginning. So how do you go from a leaky shed and a bunch of angry engineers to, world domination?
This brings us to section 2, the turnaround, because they brought in a CEO who was different.
Gates Schultz-Smith. He was a total outsider. He came from aerospace and telecom, not chips. And that turned out to be his superpower.
How so?
He looked at this tiny, struggling company, and he realized something profound. He realized they couldn't beat the Japanese giants. Nikon and Canon were the undisputed kings back then by playing the same game.
And Nikon and Canon were doing everything in-house, right? They made their own glass, their own bodies, the whole 9 yards.
Exactly.
Yeah.
Vertically integrated, they controlled every single screw. Smith looked at ASML and said, we are way too small to do that. We don't have the factories or the money. So he introduced what the book calls the aerospace model. Think about Boeing or Airbus.
Okay, let's unpack that analogy. Well, Boeing doesn't make the tires for its planes. They don't make the engines, that's GE or Rolls-Royce. They don't make the seats or the avionics. Boeing designs the system, and they integrate all the best parts from all the best suppliers. They're the architects.
So Smith decided ASML would be an architect, not a manufacturer of everything.
Precisely. Schmidt decided ASML would design the machine, but they would outsource 90% of the actual parts to specialized suppliers. You let Zeiss in Germany make the best lenses in the world because, well, they're better at it than you are. You let Philips make the circuit boards. You let VDL make the robotic arms.
That sounds really smart now, but at the time, wasn't that incredibly risky? You're completely relying on everyone else to deliver. If Zeiss is late, you're late.
It was terrifyingly risky. It meant ASML had very little control over its supply chain compared to Nikon. But, on the other hand, it allowed them to move incredibly fast. They could tap into the best R&D departments across Europe almost instantly. And it created this very specific culture. Smit was inspired by Dutch soccer, by total football.
Total football. I know the term, but apply it to corporate strategy for me.
So in the 70s, the Dutch national team played this really fluid style where a defender could rush forward and attack, and an attacker could drop back and defend. Everyone does everything.
I see.
Smith applied that to ASML. Hierarchy doesn't matter. Winning matters. If a junior engineer sees a problem, they speak up, even to the CEO. If you need to fix a cable, you fix the cable. It doesn't matter if you're a manager. It created this culture of extreme adaptability and, frankly, brutal honesty.
But they were still losing money. Right. The culture was good, but the bank account was still empty.
Oh, bleeding it. This was the survival mode era. Arthur Del Prado eventually couldn't keep funding the losses, so Philips had to buy him out. The only reason they survived the chip crash of the mid-'80s was because the Dutch government and Philips kept writing checks. But strategically, they did something very clever. They didn't go after Intel or IBM immediately.
Right. They knew they'd just get laughed out of the room.
Yeah. Exactly. So they used what you might call a blue ocean strategy. They targeted the tier just below the giants. Companies like Cypress Semiconductor or AMD in their early days. Companies that needed to expand cheaply and were willing to take a risk on a cheaper, more modular machine. They built their reputation there first.
And then came the turning point, the machine that finally saved the company.
The PAS 5500. This is the legendary workhorse. It launched in the early 90s. It was modular, it was reliable, and it was so good that there are PAS 5500s still running in factories today, 30 years later.
Wow.
It gave them the cash flow to finally stop worrying about bankruptcy every single month and start looking at the future.
And looking at the future meant looking at the impossible. This is where the story gets really wild. Section 3. The technology. We need to talk about EUV.
EUV. Extreme ultraviolet lithography, the impossible machine.
Before we get into the how, just remind us the why. Why did they need the specific type of light?
It all comes back to Moore's law. Gordon Moore's prediction that the number of transistors on a chip would double about every 2 years. That's why your phone today is a supercomputer compared to the one you had 10 years ago.
And to do that, you have to make the transistors smaller and smaller.
And to make them smaller, you need light with a shorter wavelength to print them.
Right. It's like drawing. If you use a fat Sharpie, you can only draw so much detail. If you use a super fine point pen, you can draw tiny, intricate details.
That's a perfect analogy. The industry was using deep ultraviolet, or DUV light, which has a wavelength of 193 nanometers. But eventually, they hit a physical wall. You just couldn't draw lines small enough with that pen. They needed a massive, massive jump. They needed to go from 193 nanometers all the way down to 13.5 nanometers.
That is a huge jump. That's not an upgrade. That's a completely new species of technology.
It's not just a jump. It's a different universe of physics. That is EUV.
And the book calls this voodoo physics, which I love. I want to unpack this mechanism because it sounds like something out of science fiction. You can't just buy a light bulb that shines 13.5 nanometer light, can you?
No, you absolutely cannot. This light is incredibly fragile. It doesn't really exist naturally on Earth because it's absorbed by everything. Air, glass, water, you name it. So to generate it, ASML had to build what is essentially a small, incredibly violent astrophysical event inside a vacuum chamber.
Okay, walk us through the tin droplet. I need to understand the sequence here because it's nuts.
It is. So inside the machine, there is a generator that shoots a microscopic droplet of molten tin.
Tin, like the metal.
Yes. This tiny droplet is shot through a vacuum chamber. Then a high-powered CO2 laser made by a company called Trumpf in Germany fires a pulse at that moving droplet.
Okay, so laser hits tin.
But it's not just one pulse, it's two. The first laser pulse, they call it the pre-pulse, hits the droplet and flattens it into a pancake shape.
Why pancake it first?
To increase the surface area, to make the second hit more effective. Then, just microseconds later, a second, much more powerful laser pulse hits that pancake. This blast vaporizes the tin into a super hot plasma. That plasma glows, and for a brief, brilliant instant, it emits EUV light.
And how often does this whole sequence happen?
50,000 times per second.
Wait, stop. 50,000 times a second.
Yes. They are hitting a moving microscopic target with a laser twice, 50,000 times every single second, without missing. If they miss, the tin spatters and ruins the optics, which costs millions and millions to fix.
That is insane. I mean, that sounds physically impossible.
It is arguably the most precise industrial process ever created by human beings, and that's just generating the light. Then you have to direct it.
Right.
Remember I said EUV is absorbed by glass, so you can't use lenses. Traditional cameras or microscopes use glass lenses to focus light. EUV goes black if you put glass in front of it.
So how do you focus the image if you can't use a lens?
Mirrors. But not normal mirrors. These are mirrors developed by Zeiss in Germany that are coated with hundreds of alternating layers of silicon and molybdenum to perfectly reflect this one specific wavelength. And they have to be flat.
How flat is flat?
The book uses this analogy and it just stays with you. If one of these mirrors were blown up to the size of Germany, the biggest bump on it, the highest mountain, or the deepest valley would be less than a millimeter high.
I can't even comprehend that. That is essentially absolute flatness.
It is. And it took them over 20 years to make this work. There were so many moments where it looked hopeless. The early prototypes, the alpha tools, were a total disaster. They were supposed to print chips, but the images were blurry. They called them bananas.
Bananas. Why bananas?
Because the projected lines on the wafer were curved and useless like bananas. And the power source was pathetic. They needed hundreds of watts of power to make it economical for a factory like Intel to run. They started with less than 5 watts. It took hours to expose a single wafer. It was like trying to fill a swimming pool with a teaspoon.
And amidst all this high-tech robot laser stuff, there's this great story about Joanne in the book. A very human element.
Joanne's hands, yes.
Yeah.
In San Diego at the Cymer facility making the light source, there was a specific component, the nozzle that shoots the tin droplets. It was so delicate, so finicky, that robots couldn't assemble it properly. Only one woman, Joanne, had the steady hands to solder it correctly.
So you have this multi-billion-dollar supply chain that is literally waiting on Joanne.
Literally. If Joanne was sick or on vacation, production of this critical part stalled. It perfectly illustrates the fragility of this high-tech web. We think of technology as this automated, cold thing, but somewhere at the bottom of the stack, there's often a person with a soldering iron or a screwdriver making it all work.
Now, ASML wasn't the only one trying to do this, right? Nikon and Canon were huge. Why didn't they figure it out?
They were trying. But ASML made a strategic masterstroke with a lot of help from the U.S. government, actually. In the late 90s, the U.S. was worried about Japan dominating the tech world. There was a consortium called EUV LLC, led by Intel and U.S. national labs, to research this exact tech.
Okay.
The U.S. government effectively barred Nikon and Canon from joining. They didn't want the tech going to Japan.
But they let the Dutch in.
They viewed the Dutch as trusted allies, and ASML agreed to buy a U.S. company, SVG, to get a foothold. This effectively locked up the intellectual property. ASML bet the farm on it, while Nikon and Canon hesitated because it was so expensive and so difficult. The result, ASML is now a monopoly.
It's a monopoly built on a massive gamble that paid off. But a gamble like that requires leadership. And Section 4 focuses on the two men who really steered this ship, Martin van Brink and Peter Wennink. They're described as yin and yang.
Absolutely. You cannot tell the story of ASML without these two. Let's start with Martin van den Brink. He was an employee from the very beginning. He is the technical conscience of the company, the tech giant.
And the book describes him as intense.
Intense is putting it very, very mildly. Martin is explosive. He's direct. He has a legendary reputation for screaming in meetings. He practices what he calls firefighting. He loves problems. If everything is going smoothly, Martin gets suspicious.
He gets bored.
Exactly. He believes that only through friction and brutal honesty do you solve hard engineering problems. He wants to see the blood on the table, metaphorically speaking.
The book even mentions big behavior.
Brink imitation behavior. It's a real phenomenon inside the company. Managers would start mimicking his shouting style because they thought that's how you're supposed to lead at ASML, which of course can be incredibly toxic if you don't have Martin's level of brilliance to back it up. You just end up with a lot of shouting and not a lot of solutions.
So you have this screaming, brilliant engineer, and then on the other side you have Peter Wennink.
The diplomat. Peter was an accountant by trade from Deloitte. He was not an engineer, he was the bridge builder. They even had a nickname for him, Petroduct. A play on product, and Peter, he managed all the things Martin couldn't or wouldn't. The shareholders, the politicians, and, the feelings of the people Martin had just screamed at. He was the oil in the machine.
And they worked as co-presidents. That's so rare. Usually that's just a recipe for disaster.
It worked because they had total, absolute trust in each other. Martin ran the tech, Peter ran the business, and Peter did something absolutely genius to save EUV when the costs were ballooning.
What was that?
When they were running out of cash, he created the Customer Co-Investment Program.
This is fascinating. Explain how that worked.
He went to his biggest customers, Intel, Samsung, and TSMC, and he said, look, if you want these machines to exist in the future, you need to help us pay for the R&D right now. He got them to buy shares in ASML and invest billions directly into the research.
So he got the customers to fund the development of the product they would later buy. That's like Ford asking you to pay for the R&D of the next Mustang before they've even designed it.
Exactly. But Intel and Samsung and TSMC knew that without ASML, they had no future. So they paid up. It bound them to ASML's success. If ASML failed, they all failed. It aligned their incentives perfectly and gave ASML the cash to survive those banana years of EUV development.
So they build the impossible machine, they lock in the customers, they dominate the market. And ASML, from what I gather, they prefer to be obscure. They just want to make their machines in Veldhoven and sell them. But then the world changed. Section 5, the geopolitics.
The geopolitical earthquake.
Yeah.
Yeah, ASML was perfectly happy being a background player, but chips are dual-use technology.
Meaning they can be used for a PlayStation or for a missile.
Precisely. And as the tension between the U.S. and China ramped up, first under Trump, then under Biden, ASML found itself right in the crosshairs. The U.S. government realized that if China gets its hands on EUV machines, they can build the most advanced AI, the most advanced weapons, the most advanced cyber warfare tools. The realization was the road to AI supremacy runs through Veldhoven.
So the U.S. decides to cut China off.
But ASML is a Dutch company, so the U.S. had to put immense pressure on the Dutch government.
And this is where it gets really complicated. The Wassenaar Arrangement comes into play.
Right, that's an international arms control treaty. The U.S. used it to argue that EUV machines should be treated like nuclear centrifuges, like weapons. They pressured the Dutch Prime Minister, Mark Rutte, to revoke ASML's export licenses to China.
And they had a trump card, didn't they? The de minimis rule. I found this part just terrifyingly effective.
This is the hammer. The U.S. said, look, your machines use U.S. parts, the light source from Cymer in San Diego, certain software components. The de minimis rule says if a product contains more than a certain percentage of U.S. content, even if it's made in the Netherlands, the U.S. can control where it's exported.
So they basically said, do what we say or we shut down your supply chain.
That's the chokehold. Exactly. So ASML stopped selling EUV to China. They had no choice. But then came the SMIC 7mm surprise.
This was a huge shock to the industry.
It was. SMIC was a big Chinese chip maker. Everyone thought that without EUV, they were stuck at older generations of chips, like 14 or 28 nanometers. But then all of a sudden, they produced a 7-nanometer chip.
How? I mean, if they didn't have the machine, how did they possibly do it?
They used ASML's older machines, the DUV machines, which were still legal to sell at the time, and they ran the wafers through multiple times. It's a technique called multi-patterning.
Okay.
Think of it like using a thick marker to draw a fine line. If you draw the edges carefully, layer by layer, you can create a thinner line in the negative space between your thick lines.
But that sounds incredibly inefficient.
It is terribly inefficient. It's expensive. The yield is low, meaning you get a lot of bad chips for every good one, but it worked. And this proved to the U.S. that blocking just EUV wasn't enough.
So they tightened the screws even more.
In 2023, the U.S. pushed for even stricter rules, blocking the most advanced EUV machines, too. ASML is just stuck in the middle. They argue, look, we're like a public utility. We just make the tools. If you cut China off, you're just forcing them to innovate faster.
The oil embargo parallel.
Exactly. Japan attacked Pearl Harbor in part because of an oil embargo. If you starve a nation of a critical resource, they don't just give up. They get desperate and innovative. ASML warns that by cutting China off, the West is forcing China to build its own ASML. It might take them 10 years or 20, but they will try.
And this brings us to the vulnerability of this whole system. the book talks about the supply chain web. It's not just ASML.
No, not at all. ASML is the spider at the center of a very delicate web. You have the Zeiss in Germany making the mirrors, you have Trump making the lasers, you have VDL in the Netherlands making the mechatronics and the robotic arms. If any one of those key suppliers goes down, if there's a flood, a fire, or a major strike, the machine stops. Production for the whole world stops.
It's a fragile web.
Extremely. And it's also why copying ASML is so hard. You can steal the blueprints for the machine, you can hack their servers, but can you replicate the 100-year history of Zeiss optics? Can you replicate the specific, tribal knowledge of the engineers in Veldhoven who know exactly how to tweak the calibration by feel? China is trying, but it's incredibly difficult because it's not just science. It's tacit knowledge built up over decades.
So looking forward, Section 6, what is next? We have EUV. Is there an EUV 2.0?
Yes. It's called high NA, high numerical aperture.
What does that mean in plain English?
Well, without getting too bogged down in the optics, it basically means bigger mirrors and sharper angles. It allows the light to hit the wafer at a wider angle, which increases the resolution. It lets you draw even smaller, even more intricate details.
And I assume it's even more expensive and even more complicated?
Double the price. We are talking over 400 million euros per machine. And the physics are getting even crazier. To make this work, the wafer tables inside the machine have to accelerate faster than a fighter jet just to avoid dead time.
Accelerating faster than a fighter jet inside a vacuum chamber while maintaining nanometer precision.
It is pushing the absolute boundaries of what is physically possible. The heat generated, the forces involved, it's a complete nightmare of engineering. And this leads to something called Martin's Law.
Okay, we know Moore's Law. What is Martin's Law?
Martin Van den Brink realized that just shrinking transistors is hitting a physical limit. You can only make atoms so small. So the new goal is what he calls energy efficient performance, or EEP. The system has to get 3 times more efficient every 2 years.
So it's not just about getting smaller anymore.
Exactly. It's about getting smarter, better architecture, better software, better ways of packaging the chips together. It's a move from brute force shrinking to smart system design.
And what about the culture? As ASML gets this massive, 40,000 plus employees, can they keep that scrappy startup feel?
That is the billion-dollar question. The ASML way is based on the 3 C's: challenge, collaborate, care. The challenge part is easy for them. They love to argue. They have that famous Dutch directness. Collaborate is necessary because the machine is too complex for any one person to understand. Care is the one they apparently struggle with.
The book mentions that compliments are a rare commodity in Veldhoven.
Very rare. There's a story of a manager who created a special folder in his email just to save the 1 or 2 compliments he received in an entire year because they were so scarce. The culture is built on firefighting. You get rewarded for solving a crisis.
Which is dangerous, right? Because it can create.
It creates arsonists, people who let problems happen or at least don't fix them when they're small so they can swoop in when it's a full-blown crisis, fix it, and look like the hero. As they scale, they are trying to fix this. They know they need to reward the boring, preventative work of stopping fires, not just the heroic work of putting them out, but that requires a massive cultural shift.
And maybe the biggest challenge of all is succession. Martin and Peter are retiring.
The founders, essentially, they have left. The company is now being run by a new board, one that's more international, more traditionally corporate. Can they replace that specific yin and yang dynamic? Can they keep the good parts of the Brink imitation behavior without Brink himself? That really remains to be seen.
So let's wrap this up. We have gone from a leaky shed to the center of the geopolitical universe. What is the big takeaway here for you?
For me, it's the physicality of our digital world. We talk about the cloud or AI, like there are these ethereal, magical things floating in the sky. We swipe our glass screens and magic just happens. But it's not magic. It's not ethereal at all. It is grounded in heavy metal, in microscopic tin droplets, in German glass, and in Dutch engineering.
If the machine stops, the world stops.
Literally. The entire global economy relies on these bus-sized machines in these super clean rooms functioning perfectly 247. It is a miracle that they work at all. It's the most complex supply chain in human history, and it all balances on a pinhead.
So here's my final thought for you listening. The next time you pick up your phone, just look at it. Really look at it. The chip inside that phone has billions of transistors. It was made by a machine that shoots a laser at a falling drop of 50,000 times a second. It is the result of 40 years of arguments, failures, financial gambles, and just Impossible physics. It is not just a phone, it's a monument to human focus.
And it all happened in a small town in the Netherlands that nobody paid any attention to until it was suddenly too late for any of us to look away.
Thanks for diving deep with us. This is a story that is still being written, and we will definitely be watching Veldhoven very closely. We will catch you on the next one.